Programs are data. Scheme programs consist of expressions. Those expressions can either be primitive expressions, just the number 2, 3.3, true, the symbol plus, the symbol quotient. But everything else is a combination, and each combination is a scheme list. So here we have a list containing the symbol quotient, the number 10, and the number 2. Here we have the symbol not and the primitive true. The built-in scheme list data structure that we've discussed before, it's represented as a linked list with a car and a cutter, but it can be used to represent combinations in a scheme program. So if I evaluate the following expression, build a list of quotient and then 10 and then 2, what I get is a little piece of a scheme program, a combination that says take the quotient of 10 and 2. Now notice evaluating this doesn't actually divide 10 by 2. Instead it just builds a list. But there's a built-in procedure called eval, and eval takes any expression represented as a scheme list or primitive and gives you back its value. So eval quotient 10, 2 gives you the number 5. The lesson here is that if I want to write a program that generates scheme code, I just build lists. If at any point I've constructed code and I want to know what happens when I evaluate it, then I just call eval. Python also has an eval function built in that takes a string and tells you its value. What's special about scheme is that it has all this built-in functionality for working with scheme lists, and all the code is just lists. So it's easier to construct programs by writing things like list quotient 10, 2. So one of the beautiful things about the scheme language, and this is true of Lisp in general, is that it's straightforward to write a program that writes a program. Let's do that now. So I'll start up scheme, and if I write an expression that evaluates to a value, that's pretty straightforward. If instead I list out all of these things, this is the procedure that pluses the number 1 and the number 2, then I'll get a list of those pieces. But this is not scheme code. Scheme code looks like that. So the reason I have quotation here is to say that I don't yet want to evaluate the plus. Instead, I want to leave it as a symbol, and that symbol will be evaluated just as soon as I ask scheme to evaluate the whole combination. Because this is in the operator position, so it gets evaluated to the procedure that adds, and then we apply that to 1 and 2. Now, if I were to list out plus, and then have some more complicated expression here, 2 plus 3, I'd end up with an expression where this part had been evaluated already, because it's just part of scheme, and scheme evaluates the operator and its operands, and gives me back an expression that's already computed the 5, but hasn't computed the 6 yet. Okay, now let's load this small program on the right. Fact is a procedure that if n is 0, just returns 1. Otherwise, it returns n times the factorial of n minus 1. So that's a straightforward recursive definition of factorial. If I take fact of 3, then I get 3 times 2 times 1, or fact of 5 is 5 times 4 times 3 times 2 times 1. This is just a scheme program that returns a number. But I could also write a scheme procedure that returns an expression that computes the factorial of n. So this variant, called factexp, doesn't have the job of returning a number. Instead, it has the job of returning an expression. 1 is an expression, a perfectly good way of representing the number 1. If I want to build an expression out of smaller expressions, I need a list. A list containing multiply, the number that I'm multiplying, and then the expression for how to compute the rest of the factorial. So now when I compute the factorial of 5, I still get 120. But if I ask for an expression that would compute the factorial of 5, I now see how the factorial of 5 is computed. 1 times 2 times 3 times 4 times 5. So here's a procedure that returns an expression. If I take that expression and I evaluate it, then I get 120. Let's do one more example following the same pattern. First, I'll define Fibonacci number n. If it's the case that n is 0 or 1, any number less than or equal to 1, then fib n is just n. Otherwise, I have to add together the two previous Fibonacci numbers, fib n minus 2 and fib n minus 1. So Fibonacci number 2 is 1, Fibonacci number 6 is 8. How did it compute 8? Well, using tree recursion. I could also have written a big nested expression. So here we're going to change fib to fibx everywhere, in order to say that the goal of this procedure is to write down an expression that computes Fibonacci number n. And that expression is constructed by writing down a list of what operation I'm going to perform, and then applying that to the result of two smaller expressions that compute fib n minus 2 and fib n minus 1. So fib 6 is still 8, but the expression that computes fib 6 is that I add together fib 4 and fib 5, where fib 4 is an expression that looks like that. And here's the expression for fib 5. Now if I ever go through and evaluate this nested addition of zeros and ones, I get the result, fib 6. But this is a procedure that gives me back an expression. This is a procedure that gives me back a number.